Welcome to ETAP webinar, Demystifying IBR Fault Response with Parametric Modeling and Analysis. My name is Mohammad Zadeh. I'm the Senior VP of Protection and Control at ETAP, along with my colleague Owais Askari, Senior Power Engineer at ETAP. We're going to present this webinar. In this webinar, first we're going to look at the inverter-based resource model for short circuit study. And then we're going to deep dive into the ETAP model, look at the current limiter, far right through, and then we look at the special cases that sometimes the users face with the convergence of the short circuit analysis with IBRs. And finally, we move to our groundbreaking solution for automated fault analysis software. As we know, the short circuit current of synchronous generators is inherently governed by their physical attribute and construction. And we model the synchronous generators by their Thevenin equivalent for short circuit study, the inner voltage, and then the subtransient reactance. If you're looking for the immediate response, fault response of the generator. When it comes to inverter-based resources, IBRs, their short circuit response is dictated by their basically control schemes, which is defined by their manufacturers and their settings, as well as the short circuit limits of their power electronic switches. Now, still we model the IBRs in the phasor-based analysis by typically a current source or a voltage source, Thevenin or Norton equivalent. But specifically when it comes to the steady-state short circuit analysis, the industry adopted the current source model. Now, as you see on the right-hand side, we have the dynamic model of the inverter. Typically, there are two control loops. There is an inner control loop, which is a current control loop. Whether it's a grid following or grid forming, you still have this current control loop. And then the outer control loop, in case of, let's say, grid following, typically is a power control loop. Either you control P and Q, or you control P and voltage, or P and power factor. In case of grid forming, we are basically doing the voltage and frequency control in terms of the grid forming. Now, in case of IBR model, for short circuit studies, there are three options available. So we can go and model it as a Thevenin equivalent, as you see in the far left side, or you can modeling it as a full Norton equivalent. And then, as we will discuss, in case of short circuit, the industry decided to modeling it as a current source, as a voltage-dependent current source. Now, when it comes to the short circuit study and looking at the steady state values, there will be no difference from using any of these three. That's why the far right model, which is a current source, has been used so far in the industry. But industry is kind of figuring out that there would be differences in the convergence and then the voltage right, low voltage right to detection when it comes to the short circuit study. So the industry is moving more towards the Thevenin or full Norton with the shunt in the future. And ETAP is following the developments and contributing to make sure that the users experience the better analysis when it comes to the short circuit calculations of the IBRs. Now, when it comes to the IBRs, as we said, there are two things that are really important. One is the current limit of the power electronic switches, as well as the control schemes. Now, what I would like to do here in this webinar, I would like to go through the ETAP and discuss about these two and demonstrate how these two can impact the short circuit current and the analysis. So we have a full understanding when we do the short circuits of the IBRs. Now, the first thing that I would like to cover is this current limiter, which is a voltage-dependent current limit, and then the priority, power priority. Now, in early generations of the IBRs, there were voltage dependency typically that if IBRs face a very closing fault with the significant voltage drop, they tend to also drop the fault current. Means that the IBR could not inject their full capacity or max current during the closing fault. So they tend to reduce their fault current while at the higher voltages they could inject more. Again, this is all depends on the technology of the inverter-based resources, the control schemes, the capacity of the IBRs. What we have done in ETAP, we have provided a generic mechanism that user can, through these parameters, to create the typical caves that used by IBRs. In later generations of IBRs, typically there's less current dependency and IBR can maintain its maximum current at the different voltage levels. But I recommend you to always look at the data sheets. Now, if you do not have that piece of information and you have only one value of the max current, I recommend you to put all the values the same. So that gives you basically the more conservative and worst case scenario. So in this case, I have all 120%. All three values. This means that this curve is going to be 120% all the way at the V mean to 0, as well as at the V max and higher. When it comes to the IEC standard, we also have different scaling factors for different fault types. So we have a scaling factor for line to ground, we have for line to line our double phase faults and double phase to ground, and three phase fault max and mean. The way that this works is that if the max current here on this I short circuit mass is equal to any of these currents, means that the scaling is 1. There won't be any difference in this curve. But if the current, let's say in the case of line to ground fault, is 110%, means that the entire curve here is scaled by 110 over 120. Okay, means that this curve is scaled down to make sure that the max is 110 for the line to ground fault. Or if for the line to line fault this is 105, means that this curve is scaled down by 105 divided by 120 to make sure that the maximum double phase and double phase to ground fault is limited to 105. So let me put this back again. Sometimes the vendor do not provide this information for different fault types. So in this case, you put all the same value to get the maximum possible current to get more conservative result. The second important factor in the short circuit current is the power factor priority. So as we know, the IBR short circuit currents are limited and typically is slightly above their rated current. And when it comes to the fault, either as the voltage drop, if they want to inject basically current, either they have to limit their active power or reactive power. Now, which one to do, which one to curtail first, which one to curtail second is determined by this power priority. Now, we have three options. We have the user-defined power factor, which typically is not anymore applicable, especially if you're looking at the large IBRs. Maybe is applied for the smaller IBRs residentials where they only do basically a constant power factor. You can select this value, but in the larger plants that typically they follow a certain Greek code, typically it's enforced or is required to do reactive power priority, but the options are here. This means that the IBR first goes with the reactive power. If there is room available to inject active power, then IBR will inject active power. Now, how to determine how much reactive power is injected, how much active power, it all depends on the FRT page that we're going to discuss. Now, I'm not going to discuss about some of the fields here yet. We'll come back and discuss later on. The other important page and parameters that we need to discuss is the far right through. So if you're doing short circuit analysis, make sure that you pay attention to FRT page. And this is a very important page to determine the share of your active and reactive power in the system. Now, as you see here, there are two curves, one for positive sequence, one for negative sequence. Early generations of inverter-based resources, they were not required to inject negative sequence. So that's something that you need to figure out. If you have those type of generations, you need to take a look at if they have negative sequence injection. You have an option here to disable and enable. This option, negative sequence injection, is only available if you are in the reactive power priority. Okay, so if you have this option, means that the IBR tends to use both positive and negative sequence and tries to inject both positive and negative sequence injection to the system. I will discuss that, how will be the impact and why this is good, especially when you have an unbalanced fault in the system. Now, the top curve is for the positive sequence, and what it means that if the voltage of this bus or the IBR at its terminal is within a certain deadband, typically plus minus 10%, the IBR is not going to inject anything specific to short circuit. It means that it's going to follow its load flow pattern. But if the voltage falls outside this deadband, IBR is going to follow the curve or inject or absorb reactive power depending on the voltage level. Typically, during the short circuit study, we have a voltage drop, so voltage falls in this quadrant, in the third quadrant, means that we are injecting reactive power to the system. How much reactive power we inject, it depends on the basically delta V. And delta V is basically from the 100% to the amount of voltage during the fall. Let's say that if you have a 50% voltage drop, times 2, you're going to get 100% reactive power. The user can have a separate limits on the reactive current at the leading side and lagging sides, or overexcitation and underexcitation. So user can put basically those limits in case they're applicable. If the vendor has not provided most basically latest generations, they do not have a separate limit. This current typically is the same value as the short circuit limit. But if the IBR has a separate limits on the max and mean reactive currents, you can set them separately here for all positive and negative sequence and leading and lagging. We also have a separate K factor for negative sequence, as well as the angle difference between the negative sequence current and negative sequence voltage. That's typically 90 degrees for type 4 wind turbines and the solar inverters. The value can be slightly different for type 3 WTGs. Typically it can be between 110 and 150 degrees. That you can again look at your IBR manual and put the right value here. Now let's run a few cases and see the response of the IBR during the fall. The first case that I would like to demonstrate is fault at bus 33 in the system. This is a simple system that's used as part of IEEE report on modeling wind turbines for short circuit studies. You can find a report in the IEEE Explorer. Now, I've actually enhanced that model to have more renewables to demonstrate basically the challenges in case of higher penetrations of renewables. This system has more like 70% renewable penetrations connected to the grid. What I would like to show here in this system is that when we run fault, because it's kind of a weaker system, that will be more challenging and problematic when we do that. And I would like to demonstrate how we resolve those cases. So the first thing that I would like to do, I would like to run a maximum short circuit current. And when we run this case, as you will see that it says that the WTG inverter consoles failed to converge for line to ground faults. And there's other verbiage here that I'm not gonna go through it, but what is happening is that when you run with the IBRs, we are running iterative solution. It's not anymore like a conventional short circuit with the synchronous generators. And like load flow, it may not converge. And if it doesn't converge, the first things that you need to do is typically go to the IBR and increase this number, which is the maximum iteration number for current sources, to more than a number. So I'm gonna just making it 10 volts higher and 2000 and run the same basically fault. And you see that it converges. Now, this is a very weak system, and typically in a stronger system, the short circuit converges way before 200 iterations. But this is a very weak system and it requires more iterations. So make sure that you remember that if you have this kind of issue, the first thing you wanna do, you wanna go and increase that number. When we are looking at the IBR, I have about 43.75% voltage, and this means that I have about 56% voltage drop. So if I have 56% voltage drop, what happens is that times 2 is less than 120. So it means that I've not reached my current limit because of the reactive current, so I have some room to inject active power. This means that my power factor or my current angle, the angle difference between the voltage and current, is not going to be 90 degrees. You see that this is 66 and this is minus 3.58. So I have around 70 degree current difference. Angle difference means that you're injecting some active power to the system. Now let's go and increase the the gain for the FRT, let's say that we have about 56%. If I increase this, let's say to 2.5 for positive sequence, and I can do it for negative sequence as well, and run the same case, you see that now the angle difference is around 90 degrees, means inverter is injecting full reactive current to the system. And this is what's happening, means that there's no room anymore, at least for the three-phase fault, for reactive power injection. If I try the line to ground fault, where the voltage typically drops less, let's look at a positive sequence voltage here. You see that our positive sequence has dropped around 24%. So 24%, we are injecting certain amount of reactive power. Now we also have a negative sequence around 9.58, and we are seeing that there is some negative sequence injections. Now, this is really important to understand that in the FRT page, if you look at here, it says that if the voltage, the negative sequence voltage is less than 10, there should not be any negative sequence injection. But you see that there is some negative sequence injection in this case while the voltage is less than 9.58. Now, this comes to the very important aspects of the way that we model IBRs for short circuit study. Now, as you see in the FRT curve, there is a dot in the curve that's crossing the origin in both positive and negative sequence curves. So what does that mean? Now, if you look at the WEC model or dynamic models typically out there, in this case, there's a timer. In the WEC second generation model, there's a timer. And what it says that the moment voltage drops below, let's say in this case, 0.9 per unit in positive sequence or negative sequence, above 10%, there would be a flag that would be set, and then this curve becomes continuous. So this becomes continuous, and what happens is that if the voltage comes back to the deadband region again, we're gonna have a timer, and the timer is not gonna expire by a preset time to coming back to the normal case. So let's say that if that timer by default is 100 milliseconds, and if the voltage goes, let's say, below 0.9, and then we start injecting reactive power, voltage comes back to above 0.9, we're still gonna inject for another 100 millisecond reactive current according to the FRT. Now, this is what happens in dynamics. What we do in short circuit is that we are going to have certain number of the iterations. Means that as we are going through the iterations, if after a certain number of the iterations, in ETAP, our default is around 6. So if by 6 iteration, if we go outside of the deadband, we inject. If we come back to the deadband region, we stop injecting the far right through current. Now, after the 6 iterations, if the voltage falls, going outside the deadband, we're gonna lock the voltage right through or far right through mode. This means that this curve is gonna stay continuous, and we're gonna continuing injecting reactive current per this curve. So this is what's happening here. Means that during the iterations, probably the voltage has gone up above the 10% in case of the negative sequence, and that's why the curve has become continuous. And even though the voltage, the negative sequence voltage has gone down below 10%, we still continue injecting negative sequence. And that's what typically happens in the time domain as well, because of the timers and the controller scheme to avoid toggling. So keep in mind that what you see sometimes may not match, but there are some details involved on how we implement the short circuit current calculations. Now let's try to look at the other parameters that can impact the short circuit current of the IBR. So let's start with the crowbar activated under fault. So if you have a WTG type 3, only WTG type 3, you're not gonna see this under the WTG type 4 or in the inverters. So only WTG type 3, you have these settings that if you want to see the short circuit current, if the crowbar is activated, you can check this. You can put your crowbar resistance, all the currents related to the WTG when the crowbar actually bypasses rotor of the wind turbine. Let's reduce this crowbar resistance to around 5%, let's say, for the sake of this study. Now let's look at the results. As you see, if you look at the three-phase fault current, the fault current you see there is around 15 kiloampere, which was higher than actually the IBR short circuit value. And this is because of the IBR WTG type 3. Now it behaves as a, if you look at the FLA is about 8 kiloampere. Now it behaves as a induction machine in this case. Other parameters in this page that's going to be impactful is the auto trip. Now, auto trip is basically to emulate the behavior of the IBR for right through curve. So in terms of the right through, we have two curves. One curve is about how much reactive current to inject, as you see in the FRT, but there's another curve that's typically, you can find it in the rule books in ETAP, still not used directly in the short circuit calculation. Maybe in future we add that, but basically what it says is the inverter is allowed to trip after a certain amount of time if the voltage falls below a certain value. So let's say a certain Greek codes or requirements that comes defines those curves that the IBR should ride through without tripping if the voltage falls within, let's say, these two curves. Now, in the short circuit calculations, if you want to capture the far right through, basically the timing aspects of the far right through, you can go to the auto trip, and if you select, you say that if my voltage is below 50% and then the trip time is 0.116, you can define the trip time. What happens is that if you run the mean short circuit current, and if the voltage is below 50%, then the IBR is going to be excluded from mean current injection. Let's try that. So as you see here, that because my voltage was below 50% during the first few iterations, the IBR actually tripped. You see that here we have this trip time. If I come back to the short circuit, if the voltage goes below 50%, is gonna trip, let's say at a certain time. That is 166. Now, typically the mean current, we are looking at 30 cycles, which is above the 166 seconds. So the IBR by that time is tripped, and you see that you don't see any current contribution. Now, there's one more parameter left in the short circuit page, which is this. Let me just uncheck the auto trip, this control adjustment angle that I'm gonna discuss now. Now, before doing that, what I would like to do is that go ahead and remove the fault from this bus and put the fault on bus 11. When there is a fault in front of the IBR, as you see it, this fault, if it's a three-phase fault, is going to bypass the IBR. Means that it's going to kind of isolate the IBR from the system. So the entire IBR injected current is going to go to the fault at the bus 11. Now, if the X by R ratio of the, let's say, the transformers, lines, cables, whatever is in front of the IBR does not match the angle difference between the voltage and current injections of the WTG or IBR, then we're going to have a problem, because basically the network dictates that there should be a certain angle difference based on the X by R ratio of this impedance, while the IBR wants to inject their current based on a different angle difference. So this can create on some sort of an angle rotation or instability. Now, to resolve this issue, what happens is that some vendors, they basically detect this case either by detecting the magnitude of the positive sequence voltage or by detecting some sort of an angle instability in their PLL and try to freeze their PLL in the control logic. So anyhow, what happens is that they try to fix something. Now, what most software vendors they've done in the last few years to address this issue is to basically detect these cases, and basically rather than using the fault voltage to determine the current, they use the pre-fault voltage to determine the current angle. This way you get some sort of a stability or convergence in your short circuit studies. Now what will happen here is that if I run the short circuit, let's say I run this max short circuit, in this case, what you're gonna see is, let me just make sure that I show the three-phase fault. You see that I have a zero voltage and angle here because fault is at this bus. Now you may say that the voltage is really low, 23%. So if voltage is 24% with the IBR K factor, your expectation is that you go full reactive power. But you see that there is a angle difference is not actually 90 degree. And the reason for that is that the ETAP detects that in this case, the IBR is bypassed by default. So the voltage is small. So IBR wants to inject exactly 90 degree, but what happens is that the X-bar ratio of this path is not matched with 90 degree angle. So what will happen is that the ETAP is going to use the pre-fault voltage, which is 0 degree for this case. So if the voltage is 0 degree, the angle of the current would be minus 90 degree. Okay. So ETAP considers the transformer phase shifts, the angles, and take care of that. So in this case, you see that the angle is minus 90 degree. Now, at the fault location, what you see here is that you get minus 90 degree from here and minus 50 degree from this side. Now, all depends at what time the IBR freeze their PLL and what they do. Some IBRs may not even freeze the PLL and continue rotating the angle, and you may have a kind of a higher frequency or lower frequency current injecting to this bus. Now, you may say that, okay, I'm interested to get the maximum fault current here. I'm getting 0.6, about 1.2 from here, and 0.48 from this side. Now, this current is minus 50, this current is minus 90. So you see that is a vector sum. Now, in order to really, if you really want to get a worst case, you may say that if I go to this IBR and use this controller adjustment angle. So if I go here to this short circuit page, there's a parameter here, controller adjustment angle. So if I put minus 20 degree here and press OK, and again run this max current here, you see that nothing happened. Now, if I go to a study case, there's a setting here under the standard page. There's a WTG inverter control adjustment angle. And if you set it to individual WTG inverter and rerun this case, so what will happen is that that angle minus 90 now is shifted by 20 degree. Basically, we assume that the pre-fault voltage, rather than be 0, is now actually plus 20 degree. So this becomes minus 70, and you see that this actually increased to 1.7. Now, from here, you see that if I go and increase another 20 degree, it becomes aligned. So if you really want to get the worst case condition, in this scenario, this probably should be around 40 degree. And if you run the max case here, you see that this is gonna go minus 50. These are around minus 50. You get the highest 1.74. Now, keep in mind, you may see that the difference, it was about 0.1 kilo ampere, may not be a big deal. And keep in mind this, what angle comes really, we don't know in terms of what will happen in the field, because it all depends on the timings, on the control logic. But in a software domain, if you really want to get the worst case for your arc flash calculations, for your short circuit calculations, you can go and play with this variable to get your maximum current. But keep in mind that the difference is not going to be that much. We're talking always about a small percentage. Now we talked about this case. Let me share back my presentation. Again, the case of these angle rotations, it typically happens in case of the fault close to IBR. Now, if the fault is in front of the IBR like this, what ETAP does, ETAP is gonna bypass it. It kind of detects this, and it's gonna always use the pre-fault voltage. Now, if the fault is not on the path of the direct path of the WTG or IBR, and rather is maybe an internal fault in your plan, like the test bus that I have here. So if I have a fault here on this test bus, and I'm trying to run the fault analysis, you see that the IBR has a path to the system. The path can be a strong connection or a weak connection. And depending on whether it's a strong or weak, you may have a different situation. It may converge, it may not converge. Again, it all depends. Now, here, if I run the fault, at this case, I remove that angle, the 40-degree angle we added. Now, if I run this case, you see that my basically voltage is 1.3 volt, 0.3% voltage. And the current angle is minus 90. What this tells us that ETAP froze basically the angle. Means that rather than using the measured angle, is using the pre-fault voltage angle. And the reason it's doing that is because voltage is really small. Where we point the settings related to that, under the option preferences, there are certain settings here. There's a three-phase fault setting, line to ground, line to line. And as you see here, we have a setting that if the positive sequence voltage is less than 10%, use the pre-fault voltage. So that's what's happening. You see that if the voltage is really small, it means that the chance of angle rotation is really high. And if you just run it as it is, you may have a problem of the convergence. Plus, the actual IBR in the field probably freezing PLL, or make sure that the angle of the basically PLL doesn't rotate that fast. So we have some settings here that you can play with it, okay? So you can either put all of them the same number for different fault types, or you can set them individually. Again, we have given this flexibility because depending on the vendors, they may have a different logic. You may not know exactly what the vendor is doing. I totally understand that. So in these scenarios, if you don't know, just use the default settings of ETAP. Now, if there is a convergence issue, it doesn't converge, make sure that you increase this value to maybe up to 0.7 per unit. We have heard many vendors use 0.7 per unit. You can use up to that to basically freeze the PLL to make sure that the short circuit solution converges. With that, let me go back and bring my presentation here. So we discussed about the fault close to the IBR, some of the settings. You also can have this connection to the weak system. It can be same cases, especially if you're doing line to ground faults, positive, negative, zero sequence networks together with some fault impedance. It can create some convergence issues sometimes. ETAP do lots of internal stuff to make sure that the solution converges. And make sure that you have the convergence, especially when it comes to the large networks with lot IBRs. Now, if you face some issue, again, you can play with the number of the iterations, with those settings in the option preferences. And if you face some other issues, please contact us through the customer support, and we'll help you to resolve the issue. Now, in future, we're gonna move to more advanced methods for short circuit calculation that improves the convergence and make sure that we have a better visibility on what's happening in the short circuit calculation. So we talked about the enhanced IBR model for better convergence. We're going to have more options for FRT curve terms, detection and injection options. Here, as you see, there's only one type FRT curve. There are new FRT curves that's coming up that has more like a continuous curve with the hysteresis, which does not require any locking or unlocking. So that's something that we are working on. Then there would be some also improvements on the options for the detection and injections of the right now is all about positive sequence, which is most of the cases used by vendors, but there would be options for using the mean face-to-face values for detections or injections of the far right true characteristics. So I have that sympathy with the users that it's really difficult to go through the manuals of the vendors and pick up those settings and understand how to match that with ETAP. And industry has recognized this challenge, and recently there is an initiative in the power system industry to generate a black box model for inverter-based resources where the vendors of the IBRs working with the software vendors to create a black box model for steady-state short circuit analysis. Still, there are going to be some settings, but at least it's going to be really easy that if you know the settings of the IBR that you're going to putting into the field, If you have the black box model from the vendor, then you can put it in ETAP and you run your study. So stay tuned that in future, we're gonna also support a black box model for short circuit analysis as well. Something is also, as we transition to the next topic of this webinar, as you see that when it comes to the IBR, the performance of the IBR during fault is heavily dependent on the IBR control logic and settings. So it's really paramount need to diligently collect and analyze all the fault events with your renewable system and analyze them. Okay, so that takes us to the next topic, that ETAPS offers a solution that automatically collects, downloads, collects all your COM files, fault records from your relays, fault recorders, and automatically analyze them to detect where the fault is, what's the fault types, what are the different quantities, and extract certain values to check your IBR behavior during the fault. With that, I'm passing to my colleague Uwais Askari to talk about automated fault analysis software.
Hi everyone, I'm Uwais Askari, a senior power engineer at ETAP. Today, I will delve into ETAP's automated fault analysis system, or AFAS, and I explore its capabilities and features. I'll demonstrate how AFAS efficiently enhances fault event analysis in systems with inverter-based resources, or IBRs. AFAS is a model-driven software that automatically collects disturbance records throughout the system and provides crucial information for system operators. By leveraging the model data, AFAS delivers a comprehensive report of disturbance analysis and system dynamics, enabling more effective decision making. So now let's go through the key features of AFAS solution. AFAS automatically collects disturbance records from various devices and groups them into a single incident. This process ensures that related events are analyzed together, providing a comprehensive view of the incident. AFAS calculates critical information such as fault type, location, and impedance. This data is displayed in a user-friendly web interface, allowing operators to quickly understand the nature and impact of the faults. AFAS supports both single and double-ended fault location methods for both single circuit and double circuit or parallel lines. It integrates with an advanced waveform viewer, enabling operators to see detailed representations of the electrical signals involved in a fault. This includes comprehensive calculations for phasors, RMS values, harmonics, sequence components, and more. AFAS supports reclosing events and differentiates between permanent and temporary faults. It records the sequence of operations at different levels, such as relay, bay, and substations, helping in understanding the sequence of events leading up to and following the faults. AFAS offers graphical visualization and reporting of fault locations. It can be used to validate relay settings by comparing the field sequence of operations and the digital twin model sequence of operations. Also, it helps to verify the model data accuracy, including line impedances and CD polarities. In addition, AFAS sends notifications and alarms via email or SMS, informing operators of any critical incidents. Now let's move to the ETAP digital twin model, where I have a 9-bus system set up, including two IBRs, WTG1 and WTG2, with their short circuit and controller settings already configured. So let me first go to the StarZ module and go to the scenario wizard, where I have a StarZ TS case study already set up. This case study includes a 3-phase fault at 40% of line 1. So let me go ahead and simulate this fault to generate disturbance records. StarZ TS study integrates both capabilities of StarZ protection and coordination module and transient stability module, where it performs a unified protection and transient stability study to accurately capture interactions between system dynamics and protection settings. So for more information, of its capabilities and features, please refer to the ETAP website where several interesting webinars are available. Alright, now that the run is complete, ETAP generates contract files for all the relays in the model that got triggered based on their triggering conditions. For example, here I have L1 Thumb relay and L1 Weber relay, which are protecting the faulted line 1. Let me go to the project folder where the contract files are generated. So these are the contract files for a three-phase fault at 40% of line 1. Let me go ahead and open these contract files for the Thumb relay and the Weber relay. Contract files are standardized formats for recording transient data in electrical systems, which help in analyzing the performance of protection devices. They include information about analog channels, digital channels, sampling rate, and more. Here is the trigger time of L1 relay. As you can see, it's 531 millisecond. And here for Thumb relay, I have 523 millisecond, 8 millisecond difference between the two. AFAS looks at the trigger times and group those contract files that are within a configurable time of each other to create incidents. By default, this time is set to 1 second. So these two contract files, which are 8 milliseconds away from each other, will definitely belong to one incident. Also, AFAS automatically synchronizes these contract files to perform double-ended fault location algorithms. All right. Before analyzing these contract files with AFAS, let's visualize them using Waveform Viewer. Waveform Viewer is an application integrated with AFAS where it provides comprehensive visualizations of disturbance records. So let me go ahead and bring in the contracts that I just created. So this is a Thumb relay contract file. As you can see, Waveform Viewer shows the instantaneous current values and voltage values, and also it can show the digital signals, including trip signals and other digital signals. And these are the secondary values. The user has access to display the primary values as well. Also, they can go ahead and display the RMS values, phasor values, frequency, or harmonic values for diagnosing power quality issues, reactive or active power. They can also define some user-defined variables and display them on the charts. So let me go ahead and bring in the sequence component values for the voltage. So I'm going to go to the phasor part and go to the primary and select the positive sequence, negative sequence, and zero sequence of voltage. All right, so as you can see here, the negative sequence and zero sequence are negligible because it's a three-phase fault, and the positive sequence value drops from 70 kilovolt to 27 kilovolts, which is about 60% drop in the positive sequence voltage. I can also go ahead and go to the phasor part, to the different chart, and to the phasor part, remove the current signals, and also go and show the I1 angle and V1 angle. So I'm going to go to the angle and bring the I1 angle, not this one, the positive sequence I angle and the V1 angle. All right, so as you can see here, the angle difference between I1 and V1 during the fault is about -73, -12, which is about -85 degrees. This information is crucial in evaluating IBR performance during a fault. Accurate analysis of these signals helps ensure that the IBRs are performing optimally and meeting the grid code requirements, which is essential for maintaining system stability and reliability. Additionally, Waveform Viewer handles multiple contrast files simultaneously. This allows users to compare data from different protective devices, such as contrast from both ends of the line. So let me bring in the other side contrast file, the other side of the line, L1 Weber. So I can display, for example, the voltage values for both ends of the line. So I'm going to remove the selected quantities. First, in the thumb event, I'm going to go to the phasor values and bring in the, let's do the voltage values, the uh, primary values for voltage A, B, and C, and the same quantities for the other event for the Weber relays. So then you bring them. So as you can see here, I'm able to look at the multiple counter files at the same time from different ends of the line. So this capability allows for detailed analysis of multiple counters simultaneously, which is very useful for thorough fault analysis. All right, now I'm going to send the counter files to AFAS using a training simulator application to test AFAS in offline mode. Keep in mind that AFAS can be run in online mode or real time as well, where instead of training simulator, an FTP driver is used to automatically download the counter files from protected devices in the field, and a notifier application sends notification to the AFAS engine to automatically process the counter files. Now I'm gonna go ahead and run AFAS service engine and send the counter files to the AFAS engine. So I'm gonna send counter files one by one. And as you can see, the AFAS engine creates an incident number 796 at this timestamp, and it provides brief fault location results in the app console. Detailed fault analysis results will be available in a web interface called eWeb. AFAS results are displayed in eWeb interface. eWeb leverages Windows Active Directory for authentication and includes a user access management tool for role-based authorizations. It can be accessed via the internet or a secured network, ensuring flexibility and security for AFAS data. All right, let me log in and go to the AFAS page. AFAS automatically archives incident data as it receives. So you can search by date and time and find the incidents that you're interested in. So let's sort based on the incident number. This is the incident that I created earlier. The user can right-click and add labels to the incident or view the incident using waveforms in the eWeb environment as well. Let me hide the event section to only focus on the incident results. The first tab shows field sequence of operation for all the COM-thread files. So let me expand this, and as you can see, different protection elements are shown here, such as trips or different zones of protections of the COM-thread files. You can see all the sequence of events which are crucial in understanding the protection system behavior. The second tab is fault location results for different algorithms, different single end methods and multi-end methods. If you remember, the fault was placed at 40% of the line. As you can see, the different methods provides accurate results, with the most accurate one, which is the multi-end sync results, which displays 64.38 kilometer for the fault from the TOM 120 bus, which is 40% on the line. The next tab is fault severity analysis. As you can see, the fault type is identified as ABC fault. So we can see here the trigger time and the end time of the fault period and the severity level, which is based on the configurable setting defined by the user. Here the severity is low, and also the fault current and fault voltage is shown here and calculated and shown here, and also fault resistance estimation. In the relay data, AFAS segments the disturbance record into pre-fault or load flow, fault period, and post-fault period. Let me go ahead and filter out the results for L1 thumb relay to only focus on this relay for now. Also, I'm going to go ahead and exclude the dead segment to only focus on load flow and fault. So here you can see that during fault, the voltage dropped to 40%, which shows 60% drop in the positive sequence voltage. Also here I can see that theta I1 V1, the difference, angle difference between I1 and V1 is minus 85 degrees. So these are crucial information for analyzing the IBR response during fault. AFAS also calculates the direct current and quadrature current for IBRs. As you can see here, the quadrature current during fault is minus 3.4 kiloampere, while during load flow is 53 ampere. So the difference, which is about minus 3.35 kiloampere, shows how much reactive current the inverter injects during the fault, which is essential for assessing its response and whether it meets the grid code requirements or not. These insights are invaluable for grid code analysis. Lastly, we can generate a comprehensive event report providing a complete overview for analysis and documentation purposes. With that, I conclude my demonstration of ETAP's AFAS and its capabilities. We've seen how AFAS efficiently processes disturbance records, provides detailed fault analysis, and enhances system reliability by integrating advanced visualization tools like Waveform Viewer. Thank you for joining us today. If you have any questions, please feel free to reach out.